Alright, so in this problem we cover topic 5 and topic 3, internal fluid flow and extended Bernoulli. We're using these equations to solve for the final pressure within a certain length of pipe. We can assume steady state incompressible fluid, fully developed flow, and no work. Our properties come from table A-9, and we're using extended Bernoulli equation, Reynolds equation, and friction loss equation. This friction loss equation uses an F prime that is meant for laminar flow. So we start with our extended Bernoulli equation, and we simplify because of continuity and because it's horizontal. We solve for a Reynolds number, which is 987, which we determine is actually means that the flow is laminar. We solve for F prime using our laminar flow F prime, and we get 0.0162. We put it into our friction loss equation, and we get 54 meters squared per second squared. We put it back into our simplified Bernoulli equation, and we get a final pressure of 146 kilopascals. For part B, the diameter of the pipe increases to 3 meters, so we again need to solve for the pressure at the end of the pipe. So again, it is steady state incompressible fluid, fully developed flow, no work. Our properties come from table A-9 again, and 6.2 to get the relative roughness. Again, we are using extended Bernoulli equation, Reynolds equation, and friction loss. We use our extended Bernoulli equation first, and we simplify it because of continuity and because it is horizontal. We solve for a Reynolds number, and we get 9,875, which is greater than 4,000. Therefore, the flow is turbulent. We use our F prime for turbulent flow, and we get 0.00837. We convert our relative roughness from inches to meters. We plug it all into our friction loss equation here, and we get 2.791 meters squared per second squared. We put it back into our simplified Bernoulli equation, and we get a final pressure of 197 kilopascals. In this problem, we use topic 7 and topic 3, flow through porous media and extended Bernoulli. We use this to solve for the Reynolds number through a pipe that has sand in it. The sand acts as the porous media. We can assume steady, incompressible, fully developed flow and no work. We get our properties from table A-9 and cited source 9. We are using extended Bernoulli, Ergon equation, and Reynolds. We start with our extended Bernoulli equation, and we simplify because of continuity and because it's horizontal. We put in our Ergon equation into our simplified Bernoulli equation, we get this equation. We then put in all our numbers, and we solve for our superficial fluid velocity, and we get a number of 0.00128 meters per second. We put it into a Reynolds number equation, and we get 2.115, which is less than 10, so therefore the flow is laminar. In this problem, we cover topic 6 and topic 3, pump analysis, and again, extended Bernoulli. This time we have different curves of pipe being used, and we need to solve for the pump head. So we can assume steady, incompressible, fully developed flow. We get our properties from table A-9 and from table A-4. We are using extended Bernoulli equation and friction head loss equation. We start with our extended Bernoulli equation, and we simplify it based on our assumptions, and we get a head pump equation as seen here. We solve for velocity using this equation, and we get 0.566 meters per second. We use our friction head loss equation here with all the properties from table A-4, and we're able to solve to get a head loss of 0.139 meters. We put it into our friction loss over G equation, which is seen here, and we get 1.647 e to the negative 4 meters. We plug it into our Bernoulli equation, or simplified Bernoulli equation, and we get a pump head of 1.139 meters. In this problem, we cover topic 8, external fluid flow. We are calculating the terminal velocity of a golf ball in both honey and apple juice. We also want to figure out the drag coefficient of the golf ball within both liquids. We can assume for the honey that is laminar and has creeping flow, and for the apple juice we can assume turbulent flow. For both, the gravity is constant, there's constant drag at terminal velocity. We get all our properties that can be seen in our references. We are using our drag force equation, our Reynolds equation, and our drag coefficient equation. We start with our force balance, and acceleration goes to 0 at terminal velocity. We get a force balance of our force of drag is equal to our weight minus our buoyancy force. For honey and for apple juice, we substitute in our drag force equation as seen here by the highlighted portions. For our honey, we substitute in 24 over Reynolds number for the drag coefficient, and we get this equation for our terminal velocity equation. For apple juice, we leave in our drag coefficient, and we get this for our terminal velocity equation. We solve for our radius using our equation for our volume, For honey, we get a terminal velocity of negative 0.0325 meters per second, which is because the honey has a greater density than the golf ball, so therefore the golf ball floats up. We get a Reynolds number using this equation right here of 0.199, which is greater than 0.1, for confirming that it is indeed laminar/creeping flow. We put it into our drag coefficient equation here, and we get a drag coefficient of 122.2. For apple juice, we get a terminal velocity of 0.503 meters per second. We put it into a Reynolds number equation, and we get 10,609, which is greater than 10 to the third. So therefore, the drag coefficient is constant. So our drag coefficient equals 0.18 as stated in our problem statement. In this problem, we cover topic 9, compressible flow. We have a rocket here using a converging diverging nozzle using air. So we need to solve for our final pressure, our final temperature, and our final mass flow. We can assume air is an ideal gas that has steady flow, one-dimensional flow in its isentropic, so we can use the isentropic flow equations. We get our properties for air from table A-13 and our R value from conversion tables. We use these isentropic flow equations here, our Mach number equation here, our speed of sound equation here, and our mass flow rate equation here. We first solve for our final temperature, and our T0 in that equation actually is equal to our initial temperature of 100 degrees Fahrenheit, so we get a final temperature of negative 120 degrees Fahrenheit. We use our final pressure equation as seen here, where our P0 actually equals our initial pressure of 170 psia. So we get a final pressure of 29.6 psia. We have to solve for our final density to use in the next equation, so we get a final density of 0.235 pound per mass v cubed. We solve for our V2 dot using our Mach number equation and our speed of sound equation, and we get 1,626 feet per second. We plug into this equation that actually uses our previously second density and our V2 dot, and we get 192 pound mass per second. Alright, so in this problem, we cover topics 10, 11, and 12, microscopic mass and momentum balances, boundary conditions, analytical numerical solutions to Navier-Stokes. We again have a pipe that is pushing water into a lazy river, and we need to solve for our volumetric flow, our velocity, and if it is laminar. We also need to solve for our finite differencing equation. We can assume it is relatively long length, steady state, parallel flow, incompressible flow, laminar flow, two-dimensional flow, gravity acts down, axis-symmetric, no slip-it walls, and fully developed flow. We get our properties from the common units handout, and we're using continuity and cylindrical coordinates, and our x component of our incompressible Navier-Stokes equations. We start with our continuity. We can get rid of different variables based on our assumptions above. And we get a final continuity of dux of dx equals 0. We use our x momentum, and again we get rid of different variables based on our assumptions, and we get this simplified x momentum equation here. We then integrate it all the way through to get our final velocity in our x direction equation. We use our boundary conditions of at r equals 0, our flux equals 0 because it's symmetrical, and at r equals plus or minus d over 2, our velocity in the x direction is 0 because of no slip at the walls. We put our velocity in the x direction equation into our volumetric flow equation seen here, and we integrate it from 0 to d over 2, and we get this final equation for our volumetric flow. We put in all numbers, and we get a volumetric flow of 0.192 cubic feet per second. We then solve for our velocity using this equation, and we get 8.79 feet per second. We put it into our Reynolds number equation, and we get 135,604, which is greater than 10,000, so our flow is actually turbulent, which goes against our assumption that it's laminar. For this part of the problem, we need to use finite differencing to solve for the ux of n equation. So we start with our simplified x momentum equation here, and we simplify it, and we use basic algebra, and then we put in our finite differencing equations as seen here, and we simplify again, and we get to this equation for ux of n. We then plug in our analytical equation and our finite differencing equation into Excel, and we use different numbers and different radiuses to get this graph seen here, where the solid blue line is our analytical equation, and these dots are actually where our finite differencing equation lines up with our analytical numbers.